start today's program with Torsten's invited talk. Torsten Schaub received his PhD in informatics from TU Darmstadt and his habilitation from the University of Rennes in France. He worked at various institutions, including TU Darmstadt, Ria at Rennes, and University of Angers. He is currently a professor at the University of Potsdam and an adjunct professor at Simon Fraser University in Canada and Griffith University in Australia. Since 2012, Torsten Schaub has been a fellow of ECAI, and his research interests range from theory to applications, system development, in answer-set programming, as well as relational answer-set programming to other paradigms. So he's involved in many aspects of answer-set programming. And today, he will tell us about experiencing answer-set programming at work, today and tomorrow. So let's begin.
Well, thank you for the nice introduction. Let's ask Mike whether I need a mic. It's okay like this?
For me, it's okay.
Yeah, if not, just yell at me and I take the microphone because you know I can't coordinate my laser sword with the microphone. Anyway, thanks again for the introduction, and thanks also to the program committee for inviting me here to talk. This, of course, is a very great thing. Anyway, so I will be, as you see, I will be talking about experiences, and of course, experiences are something very personal. And that's also why I just put my name on this slide, because of course, you know, this is of course in Potsdam we work really in a group, and this is of course the work as a group. But in this way, since I will be making some bold statements here and there, in this way I'm the only one today. So this having been said is, talking about experiences, I will more or less tell you about what we experience when doing application, what we experience with our tool, and the whole thing will just be a pretty Potasco-centered perspective. So I will not bother too much about explaining the left and the right. I will rather raise issues and offer you some research challenges to work on in the future. Okay, so the outline will just be somehow straightforward. I will be first give you a slight introduction just about the field and everything like that everybody is on the train. And then I will be more or less talking about 4 challenges: modeling, solving, optimizing, and reacting. And just wrap up in the end. So, however, of course, talking about all 4 of them is not possible, so I will actually put my emphasis on solving and rather sketch the other 3 challenges. So this is more or less the outline of it. So let's start with this. So I think if everybody, not only in our community, not only in AI, even in computer science, wants to do problem solving. And what we do normally, we have this commutative diagram, we want to solve them by mapping the problem on the computer. There are, of course, various ways to do that. You can do this by just posing the problem, or by saying actually how to solve the problem. And the second thing, how to solve the problem, is what we understand as traditional programming. So what you do is you have your problem, you program more or less a solution path, so something that guides you to the problem. Like think of an imperative programming language, and then you have a program, and since you have already programmed the way the problem should be solved, the computer merely needs to execute things. So you have there's a fixed execution model. This is a pretty straightforward thing to do. The other thing here is, what is the problem? There the idea is that you do not describe this path to a solution by programming it, but you only model the problem in a formal way that more or less the computer can understand and from which you can extract a search space, and then you leave it up to the computer to investigate this search space and to find this path to the solution. So these are, I think, the two different ways, and I think it also nicely reflects, I think, the ICLP community, where we have people that are interested in programming, like Prolog, and people that are interested in merely describing the problem that you have in ASP. Okay, so somehow these are in ASP, like if you talk about declarative problem solving, this is more or less the holy grail that this sub-community is looking at. These are the 3 issues: modeling, representing, and solving. So just to sum up, and for those of you who had a hard time last night, this can be somehow a way to exit for you. So what is ASP in a nutshell? It is a declarative problem solving approach, as just mentioned. And it has I think two key features. First, it has a very rich yet simple modeling language, where of course simple is debatable. and it has high performance solving capacities. And if those of you who are familiar with SAT, well, actually the solving capacities are at eye height with SAT, but what it adds to an approach like SAT are modeling capacities. And this has certain consequences. It makes things more difficult. And in particular, the biggest difficulty that you have compared to SAT, as Prolog, you have users. So in ASP, as with Prolog, we have end users. We have people sitting at the machine modeling something. In SAT, you always need someone who compiles your problem by Python, C++, whatever, into Dymex. No one will sit down, have an idea in the morning, then type in some Dymex and give it to the SAT software. Okay, this modeling thing is something that is a really distinctive feature, and that is something that one has really to keep an eye on. So this actually has been provoked actually by the historic roots, where I think there are 4 of them. There are deductive databases, logic programming with negation, where actually the original semantics came from. Of course, knowledge representation and non-monotonic reasoning, and after all, for all the solving capacities, Boolean constraints. I mean, here, of course, all the credit goes to the people in SAT who really pushed this and made it an industrial scale problem solver. So from a formal perspective, what you can do with ASP, you can actually solve all search problems in NP. And actually, once you get into applications, you more and more find problems that are a little bit higher. Because you get just under constrained problem specification, you get very many solutions, and you need to impose preferences like Pareto efficiency or inclusion minimality on the problems and select those ones. Because these are structure oriented. You cannot just do cardinality things that have lower complexity. So this is what you're going to get formally, and actually, as I said, this gets more and more important. And the solving technology under the hood, meanwhile, is very versatile. I think this is actually the nicest thing about ASP. It's not just good for ASP. Since it has to cover so many aspects of declarative problem solving, it's also good at, of course, SAT solving, at actually finite model generation, automatic theory proving, pseudo-Boolean solving, and as you see here, for instance, just as a witness for this class, has been able to score first place at all these different competitions, and not just ASP. And then the ultimate consequence is that ASP embraces more and more application areas, and as such, more and more users. So actually, to be honest, this is one thing I underestimated right at the beginning when we started our systems. We have now so many users, and it takes a lot of time to do that. But anyway, I think for the community, this is the big thing, because now we have more and more users that grab ASP tools and take them off the shelf without us knowing. There's not someone from the ASP community involved. And what often happens is they just model something, they're excited about it, but then it doesn't scale. This is more or less the issue I wanted to bring your attention to. This is something we have to work on. And this is also something that we have to find a good balance. So for instance, the SAT people, well, I think in SAT the community is a bit different in the way that you have a lot of people from electrical engineering that have an engineering background, a systems background, and of course there's tension in this community, but there are people who really look at the implementation, and then people in the theory also look what actually does that mean. So Vladimir and Amelia just had this nice paper, The Semantics of Gringo. So we released actually Gringo, and we thought the decision was we release it before we do a proper documentation. Now people just work on understanding what it does. And in SAT, there are so many things that people do not yet know actually how it works theoretically. They just found it out experimentally. And I think we need all these two ends to work in view of scalability and in view of declarativity, as I will show. Okay, anyway, so how was all this brought about? There was actually a shift in paradigm. So I think traditionally, actually I grew up in an automated theory improving group. My supervisor was Wolfgang Biebel. This was first order theory improving. And Prolog was also in this spirit. You provide a problem specification, and the solution is given by a proof, by a derivation. And of course, the central operation is unification. So if you look at model generation-based approaches like SAT, you also provide a specification of the problem, but then a solution is given by a model, by an assignment to the variables. And actually, credit for this goes to Henry Kaus and Bart Selman, who published this in '92, who actually, talking to Henry at the time, actually years later, he said they were just looking for benchmarking problems. And what they did is they then represented planning problems as propositional theories, and so that models and not proofs represented the resulting plans. And then they were very surprised at the time that this was competitive with state-of-the-art planning systems. Really big surprise. And actually, when I was at the talk at the time, and I was coming with this first order theory background, suddenly, oh, propositional logic works. It was a real positive shock. I don't know how you would say that in English properly. Anyway, So, but this has a big consequence, because suddenly, everything you got a different perspective on things, and the different perspective is, of course, everything is now, if you follow this, it's a constraint satisfaction problem. So there's no theory improving necessarily. Of course, that solvers do resolution underneath, and there's theory improving things, but you really look at things from a constraint satisfaction perspective. And if you look at then what has been done in the theory, this has already been around. These are just logical theories, and you see here, for instance, we have set where you have propositional theories, you associate models, and you can do this as a CSP problem. Here you have non-monotonic reasoning, where in default theories you always represent solutions as extensions, different sets of solutions. And here's ASP, where you have propositional programs. So this was more or less around and was there, but this really was a drastic shift in the view of things. And where ASP, of course, is not just propositional programs, nowadays you can do this with all logic formalisms, more or less. You can do propositional theories, first order theories, but what really is a distinguishing factor is this notion of stability, that more or less formalizes something that I would say goes back to databases, where you had to implement the closed world assumption, then in Prolog with the negation as failure operator. This intuition is, I think, nicely fixed with the notion of stability. So if this is somehow ASP in general, then in practice things more or less boil down to first order programs over the Herbert universe, and you look at stable Herbert models. And after all, what you do is you take these guys and you compile them back into propositional programs, and then you solve on the propositional. But I think all of you know that. Okay, so let's look at the differences just to sum up a little bit. That's my view, and actually if you look at ASP with respect to Prolog, you can view it as a representative of a theory improving approach, but of course here in this community we can just take Prolog as a nice example. Of course, you have model generation on one side, query orientation on the other. Hence, you have a bottom-up approach, a top-down approach. But I think the first real difference is that here you have a programming language, and this is important, because if you give someone a programming language, you have to give the user control. He has to be able to control the program and what is happening in the machine. And this is something, if you have a modeling language, where you want to let go. Where you say, okay, I specify it, but I cannot control the execution. I do not want to do this anymore. Just, if you forget about ASP, think of databases. So writing down your ancestry in a database should not change some of the solution. You just model. You want to dump your knowledge. So what they have, of course, of common, also due to but I think it's also a great way to get constructive notions right, is a rule-based format. But then again, things differ due to the computation. But here, unification is the driving operation. Here you have instantiation. Of course, instantiation is also the big bottleneck. This is, I think, why unification was invented at the first place, because you couldn't just in first-order theory improving use Herbert's theorem to do it. And as a consequence, modeling is different. So actually, I'm the one who suffers, I think, in my group most of it, because most of the guys, otherwise they were directly introduced to ASP. So, for instance, the typical thing is, how do we represent a list? And then the counter argument, actually, you do not want to represent a list, you want to represent an ordered collection. Okay, so an ordered collection in Prolog, it's a list, it's more or less a nested term. What you would do in ASP, however, you would keep the representation flat. You would rather think in terms of a database or a table, in the sense that you have a predicate symbol with two arities. One is the element, the other is the position, and you would keep it flat. You would not go into function, because in the end you need to be finite. So you have to be very careful with function symbols. You can use them, but careful. So in a way, modeling also here, there's a big difference that in ASP you want to stay flat, while in Prolog normally you want to go deep because you have unification. Okay. Complexity-wise, of course, you have a programming language. You are Turing. You want to be as powerful as a Turing machine. In ASP, you aim at combinatorial problems, but actually, through the back door, you are Turing complete as well, because the grounders, the systems that we use for instantiating the programs, they use function symbols in an unrestricted way. So in principle, you can code a Turing machine in there. It's just that you do not give limits in modeling, but that's not the goal. Okay, you should not use this as a programming device. Okay, so this and inside it gets a bit more elaborate perhaps, because there things are afterwards perhaps a bit closer. You have, of course, also a model generation approach bottom up. The logical foundations are of course different. While here you do this classical logic, here you have a constructive systems, logic of here and there, for instance, and you can go, this traces back to other work by Gödel and Heidel. And as a consequence, here you do open world reasoning, while here you do principally closed world reasoning, but you have this nice concept of a choice rule where you can exempt certain atoms from having to be proven. This way they are also subject to the open world assumption. So then the first big difference, that's the semantic. The second big difference actually is that there is a modeling language. Somehow people in SAT don't care about the modeling language. And somehow if you look at it, that's completely clear, because SAT has been really driven by people in computer-aided verification. The best SAT solvers, I think many of them are still built in electrical engineering departments. So as a consequence, these guys, they have their hardware description language. They have their modeling language for modeling things. So the only thing they want is a back end, so they compile things into diamonds, and that's the way it goes. It's not necessarily that that's what they want nowadays, but this is my view on their historic development. And of course, grounding in an open world setting is much more difficult, because you can't do that many simplifications as you can do in a closed world setting. Because in a closed world setting, at some point you know, oh, now I have seen all instances, and all the others I make false, so I can do substitution. You cannot do this in an open world setting. Okay, the other thing is that in SAT, people are interested in satisfiability. While I think in ASP, given the influence of knowledge representation, you want to have complex reasoning modes. You want to have satisfiability, of course, also enumeration and projection, and you want this to run in polynomial space. Because SAT servers, when they do enumeration, normally they run in exponential space. So this is something that is very dear actually to this community. You want to enumerate solutions. You want to compute the intersection, you want to do optimization. So right from the beginning, the S-model system that was developed in Ilka's group had optimization at its fingertips. That was very important. So many applications that we have nowadays, for instance, biologists ask, oh, give me the intersection of all optimal models. No, optimal is some sort of subjective function, objective function, sorry. So, and it's really this combination that makes things attractive. And of course, you have, in SAT, you have also the MaxSat community, you have other communities, but you can't just do this, ask such complex queries or some complex reasoning modes in a SAT setting. For in ASP, this was needed right from the beginning. And of course, complexity-wise, once you have disjunctive in the head, you get to the second level, while here in SAT you stay at the first. Okay, so this is now pointing a little bit to where things come from. So modeling, I think, is definitely strongly inspired by KR. Then the logic programming, the syntax comes from the logic programming community. Everything, I think most of the things that happen in grounding are database techniques. Semi-naive, database evaluation, etc. Solving is, I think, one should just write SAT here, even though an ASP server does much more. And here the stable models, this idea, I think, is in database, is in knowledge and reasoning, in logic programming. It's everywhere. Okay. So, to wrap this up, ASP is a declarative problem-solving paradigm which is really tailored to knowledge representation and reasoning. This is one of the things that is different with SAT. And as a consequence, one can come up with this equation. I think Ilka was the first one who put this at ASP is somehow a combination of these different techniques. And actually, somehow this is not the right thing to say here, because if you talk to Benjamin Kaufman, he says, well, 10% of the source code of class is a SAT solver, 90% is something else. And what actually you can view it is an SMT approach. But SMT, where you really have different theories. You have an unfounded set checker that does negation as failure for you. You have a treatment for cardinality and weight constraints. You have something that does optimization. And you can go on like this. So more or less, it's really, you have Boolean constraint technology with dedicated inferences. So this was more or less the nutshell. So let me slow down now a little bit and look at what actually I wanted to aim at. So we set out as a declarative problem-solving approach. How far did we get? So I think one thing I would propose that something perhaps everybody can subscribe to who knows ASP a little. ASP does separate a problem's representation from the algorithms used for solving it. So you do not know whether it is solved by backtracking algorithm, by a learning algorithm, by whether it's mapped into mixed integer programming. This is not something you can control on the level of the specification. However, in terms of scalability, one has to admit, I'd say, that ASP does not separate a problem's representation from its induced combinatorics. And this is crucial. This is crucial for scalability. Because if you write your problem in an equivalent, but in a way that you induce much larger search spaces, it won't scale. The second thing is, and this is, of course, if one wants to use Boolean constraint technology, and one doesn't have to use it because one can map things into mixed integer linear program or something else, one has to see that this technology is rather sensitive to search parameters, to the way which search parameters you you set. And again, in the SAT community, this is well accepted. Well, everybody plays with it. But I think from a declarative point of view, you do not want to mess with it. You have a nice specification at the beginning, and then at some point you have to tune the solver. You don't want to do that. But here actually we have solutions. So more or less how am I doing this time, by the way? Okay, great. Good. So more or less what I'll do is I follow up some work or some challenge statements I did to the occasion of Michael Gelfond's 61st birthday. So if you want to read up on this, there's this sort. And of course, some advertisement in the book, we expanded this a little bit. So let's talk about modeling first. So let's keep it brief because I just want to raise the problem. Let's look at the n queens problem. I think everybody of you knows the n queens problem. You want to put n queens on an n times n chessboard so that they are not in the same line, row, and diagonal. You all know it. So typical, and I think that this is the nicest, I would say the nicest way to describe this problem in ASP is in such a way. You follow more or less complexity theory in a way. You put a generator, an oracle, that generates arbitrary positions of queens. This is a choice rule. You may choose no queen. You may choose a queen to put everywhere or any other subset. This is a generator, the oracle. And then you write integrity constraints that filter out the valid solutions. So here you say you need to put n queens on the board. Here there cannot be a queen in the same row in the same line, and here you cannot have the same queen on the same diagonal. I think from a modeling perspective, this is very nice. This is what I teach my students. That's the first thing they should do. So write a generator, write a tester, do it like this. But is this a good thing? Well, actually, this does not really scale. So this guy does scale much, much better. But and I think if you're used to ASP, you would say, oh yeah, that's a much nicer, and you have arguments and so on. But here you use, for instance, cardinality constraints. This is actually syntax of ASP core 2. So there must be exactly one queen in a row, exactly one queen in a line, and there cannot be more than 2 queens on the diagonals like this, and on the diagonals like this, or the other way around, doesn't matter. But this is much more efficient, and you can argue from combinatorics because actually these rules will have less variance, etc., etc. But if you have end users who have no training in ASP, how will they end up with this? That's a problem. And you see, this is somehow you can argue, well, you find your way around, you get experience, but it can also be the other way around. You can also do it very badly. So this is just taking the first encoding and adding a third argument that does nothing except adding combinatorics to the whole thing. And we cannot somehow start with this and make it better. We have no tools for that. So, and just to make this a bit more drastic, so I just punished my laptop a little bit. So this is actually the first encoding, the basic one. Then this is the one with the cardinality constraint. This is more the corrupted one. You see there are many orders of magnitude between it. And so if you mess up your encoding, you cannot gain anything in the end. That's always the first thing to do. Get your encoding right, because then you can tune the solver. Then you can do other things in the end. But the encoding is the most important part. And I think so far, if I may permit, we are a bit naive with respect to that. We just show all the nice encodings, but we can't. If you give this to an end user, they have no chance to make it scalable. And this is, I think, where what really needs to work. So I think, as a matter of fact, ASP still requires craft, experience, and knowledge. And what we need is theory and tools for non-ground preprocessing. So take a program with variables, transform it into an equivalent program that has the same answer set, at least in this term, that is much more efficient, has a much more efficient compact ground representation, and is better for solving. Because you may also reduce things to death. For instance, in the SAT community, it's well known, if you apply too much preprocessing, you may get worse in the end. You have to find the right balance. But this is already a technical remark. So, and in the end, it's, you may ask, how do we do that? Well, the easiest thing, just like SQL, whenever you launch an SQL query, there are optimizations happening right on the fly. So joins are moved, selections are done, and I think this is of course an easier setting, but in the end, and we will not get the best program after all, but there are techniques for that, and we should really follow this up. So anyway, this was my first challenge. So solving now. So solving, as I said, it's a complicated thing, and let me first introduce a little bit to how solving methods look like. So conflict-driven search. So I think all of you are familiar with DPL-based search. It's based on unit propagation and chronological backtracking. In ASP, for instance, S models did this. Modern solvers such as CLASP use CDCL. Also, it's based on unit propagation, which is more or less the workhorse and the whole thing. But then you more. You do actually conflict analysis and you use resolution techniques for this. You learn these conflicts and then you back jump to the origin of these conflicts. And then there's no notion like a choice point. There's nothing you jump back to and that waits for you to give you the next alternative. No, what is happening? The learned information is added to your problem and you just resume propagation. This is a much more complicated but much more efficient approach actually. But this is more or less how things work, but they of course have ramifications. This is more or less DPLL written down the standard way. It's a constraint satisfaction algorithm. You propagate as much as you can, then you have three cases. If you have no conflict and all variables are assigned, great, you found a solution. If you have no conflict but not all variables have been assigned, well then you have just to pick a variable and assign it a value. And if you had a conflict, then what do you do? Well, you backtrack. You unassign all literals until the last decision, and then you flip it. That's what you do. So you go one level up and flip it. Now the reason why perhaps this is not the standard way to write DPLP down, and actually this is due to, these two items are due to Martin, who really had crafted this nicely. I'm always happy about these two slides. If you switch to CDCL, you see there's almost nothing happening. The only change that is really happening if you write things down like here is down here. So what happens in case of a conflict is you analyze the conflict, you translate it by a resolution, and you add this conflict clause to your problem. And then you undo the assignments on your stack until this learned constraint allows you to unit propagation. And then you go on. So there's no choice point to jump at. You learn information, you transform it, and then you just undo your assignment in the stack until this guy allows you to propagate. Then you propagate and propagate to a fixed point. Then you another part of the search space. And this is what CDCL does. So if you look at class, and this is just to shock you a little bit about the complexity of these systems. Well, you read things in, then actually class is multi-threaded. You have all your data instruction, then you have here the solver architecture. And here you have heaps of non-determinisms. There's of course the heuristics. Then conflict resolution. So when you do resolution, when you resolve the conflict, which clauses do you take? Depending on which strategy you have, you may get very different conflicts, your performance may be very different. Deletion, because you cannot learn too much. You have to delete from time to time. Which things to delete? What is a good strategy then? The other thing is restarts. How do you restart sometimes? Because restart is really necessary for robustness. Anyway, even unit propagation, because often it happens that you can derive the same atom from with several constraints. Which one to choose? This may make a difference. And yet there are lots of non-determinisms that of course make the system sensitive to search parameters. But you know, you do not want the user to do, at least not in the, I would say in the ASP community, you do not want the user to have to do that. Okay, so as a fact, this technology is sensitive to search parameters. What we need is a robust technology in there. So, and after all, keep in mind, it's all about taming the oracle. We deal with an NP problem. If some of us invents the perfect oracle, he has not only, you can do ASP in polynomial time, and he even gets more prizes because he has proved that P is equals NP. So it's really about getting this oracle right for your problem. Good. So and again, I have to iterate, the most important thing, however, is, even though I concentrate here on the solving, the most important thing is the encoding. Get the encoding right first, and then the rest follows. So for instance, if you look at the Queen's problem, this is the internal data structure of class with the basic encoding. This is the problem with the advanced encoding, and of course there are much less constraints, and also it shows that the Queen's example is not very interesting, but the encoding is the most important thing, because this is what you present the solver. He has to work on that. Okay, solver configuration. The first thing, this is the poor man's option that you can do in class. Actually, we have pre-configurations now with version 2.1. We have just these 6 guys here, which are rather different for different problems and which show different performances. Very easy example here. Running this on the Queen's example, you see the performance, and you see, well, these are the high scores, and these are actually timeouts over here. And so in this case, if you look a little bit and you play a little bit just with these configurations, Jumpy actually will do the trick on this example. So Jumpy is the clear winner. So Frumpy is the worst actually on this example, but surprise, surprise, this is actually the default setting of class. Because the default setting of class is the most conservative ones. It only includes settings that will never harm. A typical thing is set preprocessing technique. Sometimes on ASP problems, that preprocessing techniques can really be very bad. So we don't switch them on by default, but on many problems they help. Okay, so we actually almost never use the default configuration. So the other thing here is actually chatty, and chatty uses actually 4 threads to solve things. And you see, this is almost as good as jumping. And this is actually the second option that you have. Since class is multi-threaded, the best, this is again a claim, but I'm not saying it's a fact actually. Right now, the best way to do parallel solving is to do competitive strategies. If you have several resources, you give each of the resources the same problem, and each of them works with a different strategy. Search place splitting doesn't scale that well. You have to do a lot, like global restarts, whatever, to get close to that performance. This is really the most robust you can do. And so parallel solving, what class actually has, this is just invoking class print portfolio. It has a portfolio in the middle. These are just different configurations, and if you launch into several threads, you can also configure this. This is the default thing, and you can of course insert your own configurations in there. And so what happens is, when you have several threads in a round-robin fashion, it assigns to the threads these configurations, and the crafty option just takes the first 4, because it has 4 threads, the first 4, so it works with crafty, trendy, frumpy, and jumpy on different threads. This is a more elaborate way to get more robustness in the system. Because if you don't know which configuration to choose, run it in parallel. Okay, these are more or less the poor man's options. So let's make more sophisticated stuff. Automatic solver engineering. So automatic solver engineering more or less means you do nothing. You just take a tool out of the shelf, and this tool will tell you this is the best configuration. So just to show you this again, these are the 25 solver configurations, the portfolio that we have in our portfolio solver. And what you see here is these are the runtimes on a set of benchmarks, and you compare pairwisely their performance. How do they correlate? And as you see, they are all very different. So it's not that these configurations really show the same runtime behavior. It's really very different. So you've seen some of what you can do with class directly, pre-configurations and parallelism. Now what can we do else? So there are actually 3 things I just want to highlight to you briefly. One is per instance configuration, then schedule derivation, and the algorithm selection. So let's look at the first one. So this is actually the simplest one. It's PyClass, it's more or less just a wrapper. But the idea is you want to identify a configuration that works best for a specific problem class. Where a specific problem class means you have a homogeneous instance set. And what more or less this only does is a wrapper that uses class along with algorithm configurators like SMAC and ParamLS. And this is work actually we've done together with the group of Holger Hoos, whose group did Satzilla. And so the idea is more or less, you have your set of instances, you put them there, you launch, you push the button, and then SMAC and ParamLS will run class and find out what is the best configuration for this set. And the search space for this is of course a search space that is very, very huge, are all the class options. These are, again, it even goes on here below. This is more or less the search space these systems will navigate in, and via local search methods, they will actually find the best setting in. That's what they do. But you don't have to care. You just push a button, and this will give the best configuration. Again, keep in mind, if you want to solve an application and you have to make it scale, and your encoding is good and right, and you want to tune the solver, that's a very nice way to do it. So second thing is, what do you do if you have heterogeneous instances? So, and there actually the thing is, since you do not know what is coming, the idea is you give several configurations a part of the time. And this is always better than the best solver on the whole set. Because if there is one single solver that would do it, this would be the schedule. You just run this solver all the time. So and the nice thing about this, you can use ASP for doing that. You don't have to do this local search thing. And this was actually inspired by the success of PPfolio that just did the following. It won actually 15 first prize, or 15 prize, I don't know, but most of them first at the 2011 SAT competition. You more or less take 4 solvers, run them in parallel, and the operating system will sort it out. And it was more or less just the choice of the right solvers to do it. Anyway, what we do here a bit more, we look at the ordering and we look at how much time we allot to them. So this is actually the ASP code that does it. Isn't that wonderful? ASP is doing auto configuration. So it's a multi-criteria optimization problem, and the idea is more or less you have benchmark results. This is your table of benchmarks here. And then what you do is you want to say, well, how much time do you give each solver on each unit? This is actually, you can even do this in parallel. And then you have, this is the basic encoding for this. And then once you run this, what this gives you are such slides. You say, well, I want to spend 900 seconds on solving my problem. And once an ASP will give you, this encoding will give you a schedule which says, oh, you run the default for, let's say, 120 minutes. Afterwards, you run this configuration, and this configuration. And this is again, much more efficient than using a single solver on a heterogeneous system. And you can do this actually nicely with ASP. Okay, I think the most advanced thing is Classfolio, which is similar to the Zacilla approach, where the idea is you don't know what you get. So what do? Well, you get an instance, and you look actually, you look at the features of this instance. So you use instance features to select a promising configuration. And this is done by machine learning techniques, but what a shame. So somehow, if I think we in the ASP community, we are aware of one such thing. So we are aware, oh, if the problem is tight, I do not have to do the unfounded section. But we have no other mapping things, thank you. So anyway, the idea, let's just make this precise later. So you run at the beginning a feature extractor. So you look at plain instance features, number of atoms, number of rule types, etc. Then you look at features after preparation. Is the problem still tight? How many equivalences were there? What is the number of constraint types? And then you run the solver up. We normally run it up to 2 restarts. So then you have search features. How many choices did you do? How many no-goods did you have? What type of no-goods did you have? And this way it collects 82 features. And then you have a feature vector. And then you train a machine classifier with this that will then map the features of your instance to the best configuration. So, and this is just to illustrate this. This is a big benchmark set that we clustered with 82 features, and then we did principal component analysis to reduce it to two features, just to put it on the slide to make it visible. So this way it's just 2D, but it's a space of 82 dimensions. And then we just color for each cluster the best configuration. As you see, more or less, things are in different pieces. It's different configurations for different clusters. So these features really tell you something. This is just to illustrate. And then how does Classfolio work? More or less similar to Zacilla. You have instances, you have solvers. You get an instance, you compute the features, you assess the performance, and then you train the model. Then you have a training set, and you more or less build your model. This is what you do in training. And then when you do production, actually normally you run this only once because you want to find the best configuration, but you can also use it as a solver. You get a new instance, you compute the features, you score the solvers with respect to the model, and then you run it. And that's what you do in production. And actually, Classfolio was also very successful as ASP competition in this way. Okay, so and now this is all automatic. These are things you can just use. I don't say that it's easy, and I also look at this sometimes as a bit black magic, but it's nice. You just push the button. You don't have to care about it. This is meta engineering technique that is developed by people like Holger Hosgroup and etc. But sometimes you know better. Sometimes you can tell the system what choices to make. And this is actually something we just did recently at AAAI. Then I will go a bit quicker through this because I'm running out of time. So you can actually formulate in ASP as rules with a dedicated predicate modification of the heuristics. And now you give up this declarativity because now you know there is a scoring function in this solver that scores atoms. So now actually you know a little bit what is happening behind the wall. And what you do then is you ground it, and Ringo does not know at all, but then you tell the solver, which is in this case H-class, oh, look actually in your assignment, and whenever such guys become true or false, you change your heuristics. And again, I will zap through this a little bit. I'll just give you some examples. So here, this is a simple strip spanning. I think most of you can read this. So more or less we have actions, and actions can occur at a certain time point, and then we have a frame axis, and we have to program over time. Anyway, what you can now do, you can add to this encoding a heuristic where you say, oh, I want to prefer the selection of action variables. So you just say a factor 2, whenever the scoring function is involved, you multiply by a factor 2. Or you have a level which says, oh, you always first select all action variables, and once the rest is determined, that is what you can do. And then you can also do this dynamically, almost dynamically. This is still static in the sense that you can prefer things that are closer to the this way. The factor is higher the closer you are, to the goal, you prefer things at the goal. You first want to work on the goal. And then you can define your own things, and just to show you what you can do with it, this is actually heuristics that we came up with by looking at work that Jussi Rintanen was doing. It's a dynamic, this is dynamic. So depending on the current assignment of the solver, you will get different results. The idea is more or less, if a fluent is true, and you have to make a heuristic choice, then make the same fluent true also one time before. You more or less, there's no propagation, it's just heuristics. The idea is, if you have the goal and you have to make a heuristic choice because you can't propagate, then just propagate the fluent values from the goal down to the initial situation. So what does it give you? And again, an unset problem, it doesn't really, it's neutral, but on set problems, it reduces runtime. These are authentic PDDL benchmarks, so really from the planning community. It reduces the runtime by 1 order of magnitude and the timeouts by 2 orders of magnitude. You add 2 rules to it. Okay, this is impressive. But the problem is, here there was literature, we could really benefit from this literature. There are problems with optimization problems where it's also, you just prefer things in the optimization state. But otherwise, you have to be an expert to use it. This is still a bit black magic. And of course, here you give up parts of your declarativity. But on bioinformatics exams, for instance, we were just able to boost our things by 2 orders of magnitude suddenly. But just by adding some expert knowledge in that way. Okay, now optimizing now how much time do I have now? Oh, that's wonderful. I want to right on time. That's my 15 minutes. Yeah. Okay, so the other thing that we experienced, so this was more or less then the end of this larger sorting thing, is many real-world applications involve optimization. And it's not often just objective functions. Often you need Pareto efficiency or inclusion, and sometimes you even need to combine these guys. And what we need is also theory and tools for versatile optimization. You know, you ask, oh, but there are standard things out there. Yeah, there are, but it's really, there's really a whole zoo of different methods that one can use. Let me just illustrate this. So again, I just use our tools here. So for instance, we have branch and bound optimization in standard class, but in addition, when you have multi-criteria, you have hierarchical branch and bound optimization. Then you have what actually people in Maxart pushed a lot, unsatisfiability-based optimization, and we have this system unclassed that does it. And you can do incremental optimization with iCleaner. So in addition, we have like saturation techniques that you can do that lead to an increasing complexity, like in meta ASP, but where you have to use a solver for disjunctive logic, and you can actually also use H-class to express preferences. Now, how do they differ? Well, first of all of them have to invoke the solver several times. So that's actually, while this is a challenge, that's actually what I wanted to say here. It's 1 and 2. It's really, it combines both of the things. So just look at branch and bound first. You have this type of signature where you find a model, you compute the value, you look for a better model, until you cannot find a better model anymore. So it's this set, answer. And normally, finding this guy, so there are 2 issues. One of it, how fast can you descend to the optimum? That's the first thing you have to look at. And the second thing is, how expensive is it to prove that it's optimum? These are the 2 issues. So, and this is actually more complicated on these guys. Here you have hierarchical branch and bound, and here actually learning is very difficult because you have to reset certain things that you learned under this because you have to continue. Anyway, unsatisfiability-based optimization, it does unset tests and you don't see them. And incremental optimization, well, there you can see them, unset you don't see, but at least you have these steps. And if you go then a bit further, here you actually combine an NP and a co-NP problem. So you have to do both at the same time. This is what the saturation technique that Thomas Eiter came up with in his thesis, actually. And then there is this magic thing sometimes with H-class, where you just, due to heuristics, you will just go directly to the solution that you want. And there is no free lunch here. We have problems, in particular, for instance, bioinformatics, and I think Santiago will be talking about this, where among these approaches on this specific problem, this one is not even orders of magnitude better. It just goes direct to the solution, while this guy, you never see it again. Same thing at LPNMR, we made some biological contribution by establishing a network for algae. This approach here was orders of magnitude. It was just the way to solve the problem faster than just doing branch and bound or hierarchical branch and bound. And the same actually for Linux configuration problems. So we participated with both versions in the Linux Linux software configuration competition, and this is normally the approach that is much more robust, but that's not clear. Sometimes it's this one, sometimes it's this one. And what you actually want is, again, a portfolio of things. You have to want to select automatically. But in order to make your optimization problem work, it's not obvious that just pushing the button, it will do. You really have to try these alternatives. And the reason actually, why at least with us things are still spread out in the system, this is more or less our strategy to develop software. We have an experimental feature, we create a branch, and at some point when we know how it works, then it will go back in the main branch, and then if somebody is unclassed or idling, things will die. Actually, idling will die soon. And will be replaced. Okay, then the next thing is reacting. And so here's, again, a bold claim, but intelligence, I think, is built around us. So we have sensors, cameras, but don't think of surveillance, think of assisted living where you want to help people or monitor their behavior, and it's in our pockets. You all have such a device, don't you? And there's sensor information flying in and all that stuff. And I think what makes these applications different is they are not standard in a way. So if you really want to make something intelligent, every apartment is different, every profile of the user is different. This is where knowledge-based techniques can really make a difference. Because so far, at least the things I have seen, it's a Perl script, it's a Python thing, it's a C++ thing, but it's really difficult to take it from one thing to the other and to customize it easily. I think with knowledge representation, you can make a difference, and we should really work in this direction. And so what we need, however, is since it's dynamic, we cannot just do this one-shot sorting anymore. We cannot just push the button, get a solution. And things have to be incremental, reactive, working in time with real time as well. And there's some work. So just to give you some hints, again, very from our perspective. So iTlingo did more or less the dynamic aspect, but offline. You can do planning. Then what we can do sliding windows and stream reasoning. With Oaklingo, I think we can do. We worked on this, and it's not obvious, and it's more as proof of concept thing. We can do interactive query answering, for instance, and we now actually integrate our things in ROS, and ROS is the robot operating system. It's a middleware thing. It's a free thing. Like you can think of Linux. It really takes off right now in the robotics community because it's a free middleware where people can then contribute to it. And this is actually now this leads me actually to a first real, I would say, really success story. Is the work that has been done by Zhang Peng in China. So this is actually, these are two robots, and so actually the task was the one should get a cup, the other should get some water, and the one is pouring water and the other one's cup. Okay, this is, I think, I found this very impressive, but what is really nice about this is the ASP inside. And what makes it even nicer, and this is actually why I put this forward, this was done by a robotics group who just took ASP off the shelf. So they used our tools without us knowing. It was just at one occasion I ran into the guy, or more he ran into me and said, oh, it was nice to use your tools. So, and this is I think one further step that really people use this off the shelf. That's something that I think in product has been done going on for decades, that you have commercial product system, but in SAP you can't do it. You can't give the SAP server to someone. Then you need an expert. You need at least a computer scientist or someone who does all the mapping things, because you can't be there as an end user. But here you can just do that. And that's also what we experience actually in bioinformatics. That biologists actually are very happy with it because you can show them what you do in the system. You don't bury things in code. It's not that when someone, a postdoc or a student leaves, you can't maintain the code anymore. That's the wonderful thing. And well, I think these are all arguments that when product people can just advance as well, so I'm not want to make here a bit different. But that's a really nice thing. And I know that Ezra is doing as beautiful work, but you are an ASP guy. So I think this at least was very impressive. So to sum up, so I think we are declarative, but in a certain way. We are declarative in the sense that ASP separates the problem representation from the algorithms used for solving it, but in terms of scalability, there's no free lunch. Actually, I don't know what. Some of you actually approached me also just 2 days. Oh, we started using ASP, it was wonderful, and we got great things, but it didn't scale. So how can we change the model? This is really where our problems are. So I think with modeling, we feel too safe because the first encodings look too nice. But when you then come to to more advanced problems, they don't look that nice anymore. And we don't have the knowledge really to tell someone do this and this and this, or even have a tool, push the button and do it. Then solving, I think, that's actually what I wanted to say. These methods, of course, you may not like them because it's a type of engineering that is happening, but they are free to use. So if you really have got, again, if you've got your encoding right and you want to pimp the solver, you can use these different tools and they will help you. So there's this burden, I think, has been more or less taken away. Optimization, I put this in orange because I think we are on the right track, but it's not yet converging anymore. I think here with solving, we are in pretty good shape. Optimizing things, it's still very heterogeneous. It's a zoo of different methods. I think reacting is an open but very challenging field, and I think this is a great thing for the community, because suddenly, when you react, when you work in a dynamic environment, you also get new knowledge representation questions. So what does it mean to forget information in a logic program at a certain time? What does it mean to update it? What does it mean to revise it? So now you can really do it. Because before there were just we just had theories about it and we were rewriting the program. But here the issue is also make it in such a way that if you update that you don't have to rewrite, reground your problem. Because keep in mind, we can't do unification, we have to do saturation. How can we do this? By keeping the program intact. How can we do this in a dynamic environment without losing the performance? Because if we have to reground or relaunch a solver each time, this will work for toy example, but it will not scale. Okay, anyway, so then if you like this, just you can visit us, and we try to gather the resources around ASP. And I think most of you like it. I don't think you like it, but know it. At Potasco, at SourceForge, you can download the system. They are compiled meanwhile even for Macintosh. So for Oliver, for Linux, for OS, it's free. And in particular, since 1 year, we also put teaching material up there, also open source. You can just take the LaTeX course and integrate it in your course. And as I started this talk, and I'm done in a sec, by saying that it's an opinionated thing. And I made some bold statements here, and that's why I put myself as an author, because this is group work. And Potasco is, of course, a composition of people. And I just put the list of people and also the master student that contributed significantly, and the yellow guys are just the active current group. And you see, after all, I'm German, and I'm giving this talk in Turkey, so I have to end it with umlaut. So here's a Dankeschön. That's a nice umlaut there. And since I have a French pass, Ines.
Maybe we can also say that there is this new book on ASP in practice that you co-authored, and it is also available, right?
Yes. Actually, it just came out before Christmas.
Very nice. So let's take a question.
So scalability, I guess, is still a big problem, and I see there are 3 ways in which we get hit. It's quite a great talk and a wonderful system. So one is, of course, grounding that, to blow up the program exponentially, and that's a huge challenge. So it works great for NQueens kind of problems, but then if you have a real knowledge base, I don't know if ASP technology can currently handle it or not. The other one is the fact that you have to compute the whole model. And many times you may not be interested in computing the whole model, so essentially this model generation based view actually works against you, and a proof theoretic kind of view might help you, where you're only interested in a certain goal, and you're only interested in establishing the truth of that goal. And the third one is that your entire knowledge base has to be consistent. So if part of the knowledge base is inconsistent and my query does not touch that part, I will still get hosed. So it would be nice if, as long as I operate in the consistent part of the knowledge base, I'm still able to get my answer. And that is really needed for practical systems, because you cannot really expect a knowledge base, a large knowledge base, to be entirely consistent.
Yeah, well, do you want me to comment on the individual things? Or?
Sure, yes.
Okay. So so somehow there are, I think, 2 things. So I think you would distinguish between inconsistency and incoherence. Because here actually you don't have classical negation where you just derive everything from it. It's more or less, it's just on the semantic level, you get no model. And of course this is an issue, but it's also an issue in classical sense. And actually what I call often the curse of declarativity is that since we deconnected the specification from the algorithms, we cannot apply standard debugging techniques. We cannot have a trace. And look, this is definitely a problem. And there one just has to be think a bit different. The next thing with grounding and so on, yeah, but I think this is a modeling issue. Actually, the experience we have more or less is you can take ASP to a lot of grounding is really not a big problem in terms of quantity. If you have large problems, it doesn't matter. The machinery is very efficient. It's the combinatorics. And when it really gets to a way where you're just better off with a constraint solver, because you have so many objects, like you have variance over the integers, you either use a hybrid system, and you put this part in the hybrid system, or you use a constraint solver right away.
But if I have 100 constants, then I will probably get a.
100 constants are nothing. Nothing. You see, for instance, one bioinformatics application is we have to have an optimization. So we have a model thing, and we have to import. Actually, it's an abduction problem. To import things from another. To import reactions from another organism. The number of reactions is 20,000. This is not counting some of what the powerful organism. This is not really a problem. The problems are elsewhere. So grounding, it's really the matter of keeping the combinatorics going. The combinatorics is also there in the query answering approach, for instance. So it's not the mass that hits. And your first solution?
Computing the whole model.
Yeah, computing the whole model. That's something, well, what class, for instance, has a projection option. So for instance, at least in enumeration, you can project to a subset, you will not get a duplicate solution. That's pretty efficient. And so far, this problem didn't occur for us. So because actually, you experience this not actually on multi-threaded, but when we have also a system that works with MPI and that you can run on very large clusters. So if you run, for instance, the solver on 4,000 nodes, the big pragmatic problem that really hits you is printing. Because you can't print enough. You can't print quick enough and get the solutions out. And this is, in a way, computing it is not the problem. At least these were not problems that we came across in our
Your title includes tomorrow. I'm interested in your perspective of what can happen in 5 or 10 years. To me, although there is a dedicated application area for SAD, CSP, and ASP, it seems we're running into some kind of a bottleneck, and since the major breakthrough of conflict-directed learning and focusing on engineering about 10, 15 years ago, there has been no major breakthroughs in SAD, CSP, as well as ASP. So I would like to see your view of what's going to happen in 5 or 10 years.
Yeah. Well, I know your preferred answer. Your preferred answer is get existential quantifiers in there. Yeah, but as I try to say,
the bigger picture.
as this reactive thing just hits a really big new challenging field, because after all, we gave up unification for saturation. And there are certain problems, of course, where you think we could never do it without unification, basically, or like in database, we have schemas and you instantiate them. And this is, I think, something I would really like to push, and I think we need this if we want to be flexible and dynamic. That the problems evolve over time, certain logic programming rules expire, like if you drive, certain traffic symbols expire, others, new rules come, other things expire. And how can we do that without regrounding all the time? And having the solver dynamically attached. This is, I think, for me, the big challenge, because that's the only way we can cope with the dynamic environment. We have to adapt our problems. What is also not on here, which I find is very important, in order to make things practical, we have to think about how to combine ASP with other computer paradigms in a nice way. And there's, of course, since many years, this workshop here at ICFP, ASP and other computing paradigms. There's, for instance, the work by Thomas Eiler, who combines it with description logics. So we work on how to combine it with constraint solvers, and we do some work also with people in Japan, who is Takehide, here. So we did work on this, and in particular with constraint solvers, because I think this is the bottleneck when it comes to ASP. I was just alluding to that. Is when you have variables and grounding becomes a bottleneck, often it's just a CSP problem, and you just have to have a hybrid model of them. Yeah, I think this would already give me enough for the next 5 years, let's say. But I think the basic thing is we need a shift in the community, because I think our community, we have too few people who deal with practical aspects. If you look at the SAT community or the product community, people are also get their inspiration from the practical aspects, and they are fruitful really from the beginning. So actually, in my group, since we are now faced with applications, we get so many new research problems from the application area. And this is I think a bottleneck in the community. This is the really big challenge, I would say, that we have to face. Because Vladimir remembers that there was this non-non workshop in Dagstuhl where Matt Ginsberg gave this talk, and he was the organizer and said, okay, NMR is dead. And I will leave this community, and we never saw him again. And this was very, very frustrating. But then what rescued us were S models. Because suddenly there was a system, and we got inspirations back from the system. And then DLD followed, and this, of course, answer set programming took off. But you know, it's very important as a community to survive, to have systems and to have applications. And we have too few people that care about it. That was, again, a bit political, I'm sorry.
Okay, thank you very much, Torsten. So maybe we can get the next session prepared while we take one or maybe quick question. Quick question.
So where do we stand with the M Queens problem? Imagine that somebody comes to you today and says, I want to use this straightforward natural representation, but I want to get the result fast. What can you tell him today?
Oh, actually, if I use Jumpy, I can get you 5,000 queens on the board in 1 hour.
Thank you.
Thank you. The same, Torsten.